Okay, so you probably don't hear this for the first time, but there's a suggestion in quantum theories of gravity that space-time is not fundamental. Rather, it's supposed to sort of emerge from something more fundamental that's not spatial-temporal in any useful way of these terms. Just as we're used to thinking when we think about material constitution, material objects like tables and chairs are not fundamental objects. They're constituted in some material way by something that's completely non-shared happening, something with completely different kinds of properties and characteristics. So that much I presuppose for this talk. The question that immediately then follows, and that's the sort of the starting question for this project that Baptiste and I have engaged in, is whether, just like tables and chairs, space-time might be physically contingent. Tables and chairs in their existence depend on their constituents to come together in a particular way in order to form tables and chairs, and perhaps the same could be said about space-time. So this is the thesis that we're going to defend today, that when you think about it in this way, it turns out that space-time, just like tables and chairs, is physically contingent. So that's the thesis. Now, how are we going to approach answering or defending or arguing for that thesis? Well, we use a methodology which we tend to be a naturalist methodology, and I think it's implicit in much philosophy of physics, even though it's often not actually explicated in any detail. The ansatz that we use is that we look at physical possibilities as they're handed to us by our best physics. That seems natural enough and naturalist enough. So a theory T could then be said to license a physical possibility just in case the possible world is consistent, the possible world is consistent with the laws of that theory. Simplifying a bit, we could then use the models of the theory as a guide to physical possibilities as licensed by that theory. Now, here we are bracketing some important and very deep and very, very difficult and challenging questions in the philosophy of science, such as the question what the relationship is between models and worlds, the represented and the representation. We are going to use presumably forms of idealizations, of approximations, and so on and so forth. This is actually, when you look at the details, a rather messy kind of business in which the resulting answers are really complex. So we are really helping ourselves here to quite significant simplification. We don't think that this simplification is in any way sort of problematic for the conclusions we want to draw. But if you disagree, we're happy to do so in Q&A. We also are going to bracket, in a way, the question of the relationship between physics and the special sciences. What do you really mean by naturalistically possible? What's the relationship between physics and other ways of being possible, and so on and so forth? Again, this is a whole field in which bookshelves have been filled about that. We're going to just assume sort of a physical imperialism and march on. Okay. Now, the principle we're going to use is that the state of affairs is naturalistically or physically possible following our methodology, just in case it is a model of a theory of our best physics. Again, that's not much more beyond what I said already. The question, of course, that's relevant is what is our best physics? What do we take to be the best physics? That's pretty relevant to determine that. And it seems clear that as far as space-time or gravitational physics is concerned, this is GR. GR has earned its spot as the best physics that we're certainly entitled to use. The problem is, and that's central, is that GR has severe limitations. GR cannot be the best physics of the very, very early universe, and it seems it cannot be the best physics for the physics of black holes. So there's going to be some physics where it needs to be replaced by a superior physics, and that's going to be some sort of theory of quantum gravity, some sort of theory that can combine relativistic physics with quantum mechanics, with quantum physics. Now, it may be a stretch to call theories of quantum gravity our best physics, because none of this is confirmed, as I freely admit. But the assumption is we will need some such theory, and one such theory will eventually turn out to be the best. And we believe that at least in those candidates in the running right now for that kind of a title have the similar kind of solutions in the questions in which we're interested in. So we have in a way two levels then. This theory of quantum gravity is supposed to be more fundamental than the theory of GR. In GR we have a space of models, here in green. That's the space of physical possibilities according to GR. And in blue, we have the physical possibilities according to quantum gravity. And as you can see in both cases, I have sort of shaded a region, a sub-region, a strict sub-region in those spaces in both cases, because we take it that at both levels, there are models such that they do not in any useful way correspond or are not counterparts of any other, they don't have a counterpart in the other, at the other level. So there are going to be spacetimes, relativistic spacetime models, which do not have a corresponding fundamental theory to support them. There are going to be those possibilities that perhaps once you accept more fundamental theory, you're going to discard as true physical possibilities. This is how we learn from a more fundamental physics what's actually not physically possible, perhaps. Similarly, however, it should also be the case that there's a sense in which there's models in quantum gravity which do not have a sort of a classical limit. They do not in any natural way correspond to any relativistic spacetime. That's the new physics that is going to be predicted by these fundamental theories. That's what we're going to learn about. In the parts, in the shaded parts, we assume there's going to be some way of relating these models. This is going to involve some approximations, some idealizations, some mathematical derivations, maybe some, somewhat less than fully clean by the standards of a logician or a mathematician. Physicists' work of sort of convincing ourselves that this is somehow, this model gives rise to that, and so on and so forth. The question then is, what's the nature of these models here in the non-shaded part of the blue space? Are these possibly non-spatial temporal models that do not have any space-time counterpart? A world in our methodology then consists of a pair of models. One, a fundamental model that captures the physics at the fundamental gravity level, and an emergent model that captures the space-time level. So it's a pair of models, MF and ME. Now, as I just said, graphically beforehand, there's going to be some worlds which fail to have a description at the emergent level. They just are described by a fundamental model. Now, there are no physically possible worlds just described as an emergent model. Those are going to be ruled out as physical possibilities. That's the idea. So in that sense, these models don't refer. They're sort of artifacts of the less fundamental theory. Now, if that's the sort of the setup we have, the language in which we speak, then there's two ways in which a world can fail to be spatial temporal. In a strong way and a weak way. There's actually more possibilities which we discussed discuss in a paper, which we're happy to share with you in case you're interested, but let's look at the main options here on the table. And the strong sense in which it could fail to be spatial temporal is to say if we just have a fundamental model and it's not spatial temporal in any way, the physics, whatever it is, cannot be interpreted as a spatial temporal kind of physics, and there's no counterpart at the level of relativistic spacetimes. So that's a strong sense in which this world is not spatial temporal. Of course, there could be a weaker sense then that the fundamental model is still non-spatial temporal, it has some sort of funny non-spatial temporal physics, but in some classical limit it has an emerging space-time, corresponding space-time model. So that's a weaker sense in which it's not spatial temporal, in the sense that it is sort of spatial temporal, but not fundamentally so. So the assumption is that our world would then be described by a model like this. Our world could not be strongly non-spatial temporal, because that would make it a mystery why general relativity would be as successful as it has been. And, let alone at the sort of more ordinary level in which we're so used to organize and structure our world spatially and temporally. How could we make sense of that if there's not a robust sense in which space-time emerges from whatever fundamental quantum gravity suit we have? The question then is whether all physical models of a quantum theory of gravity are going to be weakly spatial temporal, whether some of them are strongly non-spatial temporal, that is, whether there's some which just do not give rise in any way to a relativistic space-time model. Okay, I hope the setup is clear here. The principle we're going to use to answer that question is that if some physically possible models are strongly non-spatial temporal, then we will say that space-time is physically contingent. Because there's a clear sense in which it could have been the case that the world is strongly non-spatial temporal. There's not even sort of a space-time emerging. So the question is then, or the goal of the project is to establish the antecedent. So by modus ponens we can derive the conclusion we want. The methodology is then to just look at different approaches to quantum gravity and see what these theories tell us. And in the paper we've done that for two approaches. We believe that it's going to be a similar result will happen in pretty much all the other major approaches that we know, but for the purposes of today I'm just going to present you one example, which is string theory, and I'm going to be very quick here because Enrico has thankfully already basically explained a lot of what we're going to need to make the point, to show you how space-time is physically contingent given Orion string theory. So string theory, we sort of oversimplify a little bit. The fundamental entities are strings and branes, as we've seen in the last talk, which I trust most of you have been here, which vibrate within a particular 10-dimensional space-time known as the tangent space, the target space. It's important that this space-time here is in quotes because it's a priori an open question in whether that is a space-time in the sense that relativistic space-time or space-times. And the answer is going to be that that's not the case, actually. So we have to be a little bit careful here what we call space-time. Okay, now in order to recover four-dimensional relativistic space-time from whatever's fundamental according to string theory, 6 of these dimensions of target space must be compactified. That is, they must be curled up so that they're invisible to lower energy probes, because that means in our normal ordinary physics we don't see these other additional dimensions. Okay, that in string theory, we have a number of problems of actually executing that research program. One is the landscape problem. That is, there's a very, very large number of actually of producing of such compactifications. Finally, I actually see something on my computer as well. Good. The small blank problem is a different problem. It's the problem of which of these compactifications are consistent with string theory as a theory of quantum gravity. I'm not going to discuss these significant problems for the string theory approach. There's also the particle physics problem, that is, which of these compactifications are going to give rise to something that looks like the standard model of quantum physics, which of course we want to recover from the more fundamental theory, because if anything in physics is well confirmed, it's the standard model of particle physics. Okay, so now the relevant question, string theory and space-time. Now, as I said beforehand, naively you might think that space-time is fundamental in string theory, even though maybe 10-dimensional and somewhat different from what we have. And 4-dimensional space-time then emerges as some sort of approximation from this underlying fundamental 10-dimensional space-time. The problem is there are good reasons to think that this is the wrong way to think about this, and the reasons I'm not going to go over, but if you're interested, I recommend Huggett 2017 in particular to give you those reasons. As we've heard in the talk just before, there are dualities which relate different kind of string theories you can then formulate. And in particular, two things are important to keep in mind. Namely, that dualities are interpreted as relations of physical equivalence. So there are two theoretical formulations or representations or theories, or however you want to talk about this, which are capturing the same physics. That's the sort of the way to think about dualities in general. And secondly, then in T-duality, as we've seen in the prior one, it's a duality of physical equivalence which relates open strings and large compactification radii of a certain type of string theory with models of closed strings and a small compactification radius in a different type of string theory. Now, that, according to Huggett, suggests we should not think of space-time as being fundamental in string theory. Now, at the very least, it seems a spatial dimension with large radius in one model corresponds to a spatial dimension with small radius in another, even though the physics is the same. So that means there cannot, if you're a common core defender, that is, you only are realist about those elements which are common to both representations, then it seems as if you cannot be realist about at least spatial distance and topology, because these are not the same in the two models. And with spatial distance and topology gone, that's a significant part of space-time. Whatever is left is less than very different in nature from space-time, as we know it in GR. Okay, now this establishes that space-time may not be fundamental in string theory. It does not establish that it's contingent. For that, we need something more, namely that only some string theory, some models in string theory are going to be compactified such that they will give rise to models or can be related to models in GR. And if that's the case, and we give you more information in the paper, but I'm going to move on in the interest of time, if that's true, then it's also physically contingent, because then we have models for the string theory which don't have emerging space-time. Okay. The last few minutes, when did I start? About 53, all right. Okay, so I have about 11 minutes? Okay. I want to spend the 11 minutes that I have with thinking a little bit about the metaphysical implications. We're interested in the metaphysics of science at this conference, so we want to think about, suppose what I showed you is now the case. It is, we should think of space-time as physically contingent. What kind of implications would that have if that were to be the case? We call this position, by the way, space-time contingentism, namely the thesis that space-time is physically contingent. First of all, it would have an implication of physical contingentism. That is, if the existence of space-time is contingent, then any metaphysical view which relies on the existence of space-time itself will be contingent in the same way. And when you start to think about it in metaphysics, there's a lot of views in which we presuppose or just assume that there exists space-time. So these may be metaphysical views which have little to do a priori with physics. It may even be, theories of personal identity, which suppose that, fundamentally there's space-time, but there is space-time anyway at the level of persons, for instance. Now, maybe not for a theory of location, that may be more general, but even in the theory of location, paradigmatically, we would think of space-time location as an important example of that. So, there's a sense in which physical contingentism would have to be accepted quite generally. More specifically, when you think about the debate in the metaphysics of space or metaphysics of space-time between the substantialists who believe that space-time is a substance in its own right, in the Aristotelian sense largely, versus the relationalists who think that space-time is nothing but a sort of conveniently summarizing complex of relations between material or physical objects and their spatio-temporal relationships. That debate seems to be impacted if it's possible that space-time doesn't exist. So, for instance, what would that mean for substantialism if space-time just contingently exists? Well, you might think that that's not the end of substantialism, of course, because something can be a substance even if it's just contingent. I'm arguably a substance, I exist contingently, so that in itself is not maybe a problem. But you will have to start to think about what you mean by these concepts and what it is that this space-time substance needs to be, whether you need some form of maybe strong emergence for it to be the case, that it's kind of an individual substance with all the powers that the substance has, or is maybe a weaker form sufficient, or maybe can we sort of transform substantialism at the level of emergence only, because fundamentally we don't have space-time, so we don't even have to debate. What would that mean? How would that be impacted if it's really a debate at the non-fundamental level? Now, it will also depend on what you mean by supersubstantialism exactly, but if you think that supersubstantialism is the theory that space-time is fundamental, you have a problem here. Maybe that's not the best way to formulate supersubstantialism, but you have to be careful. It's not even clear what a material object is. Also, the relationalist is not just out of the woods. Because if you think of a material object as something that's in space and time, obviously it may run into the same sort of problems. But maybe you then have a more generalized notion of what it is to be a material body or a material object. But then it's unclear whether that is still, by virtue of what, this is a material object, and so on and so forth. We do not pretend to have an answer to all these questions. We don't take a particular stance. It's just about showing you how the debate is going to have to be modified if space-time contingentism holds. Physicalism, if physicalism, as is often the case, is formulated as the thesis that everything is physical, or the mental is physical, or something like that, and you think that whatever it means to be physical is to be somewhat in space-time, then all of a sudden that physicalism may itself become physically contingent. Okay, and if I have, I have a few more minutes, so let me spend those thinking a little bit more about laws of nature specifically, what the implications for laws of nature might be. So you might think, or you might ask, what are the consequences of space-time contingentism for the debate on the status or the metaphysics of laws of nature? I've argued with Vincent Lam that most of the extant analysis implicitly, directly, or rather explicitly, assume or presuppose or rely in some sense on the existence of space-time. That's a problem in both weakly non-spatial temporal and strongly non-spatial temporal worlds. In a weakly non-spatial temporal world, it just means that your analysis will only get traction at the emergent level. How can you speak of what's a law at the fundamental level, which is not spatial temporal, when your analysis relies on there being space-time? And that becomes a little bit mysterious then, because it's not clear how you can identify what's a law at the fundamental level. And presumably, the fundamental level should be thought of as law-governed, and the emergence of space-time should be thought of as law-governed. And so this then becomes a bit of a problem. But in strongly non-spatial temporal worlds, it seems as if there wouldn't be any laws at all. How could there be if your analysis just presupposes or gets any to the starting blocks of their space-time? So if you have, therefore, some form of mnomic spatial temporalism, that is the view that laws only exist where there's space-time, you will have some physically possible worlds without laws. The laws themselves become physically contingent. And that seems to lead to an interesting form of incoherence, which we call mnomic incoherence. Namely, it's the laws of physics that tell you that there are strongly non-spatial temporal worlds, which your analysis of laws of nature tells you there are no laws. So that's somehow it's the laws that mandate that there's no space-time in these worlds, but at the same time these laws do not govern those worlds because there are no laws there. So that's a form of mnomic incoherence. How can we deal with that? How can we get out of that? Well, here are some possible resolutions. Again, we're not endorsing any one of them, we're just saying like, look, you have to address that question, and here are some ways in which you could address them. One would be revisionism. You forget about your old analysis of laws, you disavow mnomic spatial temporalism, and you articulate an analysis of laws which does not depend on the existence of space-times. Maybe you think of laws as constraints, maybe primitively given, so it may be a form of primitivism still, but they're not laws of spatial temporal production in a spatial temporal arena. They're much more abstract and general and different kind of things. If you do that, arguably that's a way to get around the problem. Or you could be a mnomic pluralist. You could say, well, laws contain different metaphysical profiles in different contexts, that is, different worlds, or maybe within the same world at different levels. For instance, you could say that at the fundamental level, laws are identified by the constraints that they impose on these fundamental physics. At the emergent level, we have a different notion. Maybe we have a notion of some sort of primitive mnomic production in a spatial temporal setting or something like that as a result of that. That seems to imply a form of scale fragmentalism. There's a metaphysically quite deep sense in which the different levels would have to be governed by very different metaphysics. That is odd, but as I hope all of you agree, oddity in itself is not an argument against the position. But there is a threat of some form of incoherence again. Namely, if the spatial temporal laws at the emergent level and the non-spatial temporal laws at the fundamental level would have to have different metaphysical profiles, it's not clear how we could actually get to and identify and know the fundamental laws. Maybe there's answers to that, but you would have to address these kind of questions. Conclusion. So in our naturalistic approach to metaphysics, we use the best physics, or at least what stands in for the best physics for now, as we don't have any established theory for gravity, as a guide to what is physically possible. And if in this spirit, and of course completely defeasibly, we take seriously the space of possibilities as suggested by these theories, such as string theory, as I've used the example for that, but there would be other examples, then the conclusion that space-time is physically contingent seems hard to avoid. I wouldn't go quite as far as to say completely impossible to avoid, but you would have to argue really counterintuitive things, I think. And, as I've tried to show in the last part of the talk, if that's borne out, that would have implications for the metaphysics of science, such as the metaphysics of laws, where an analysis not relying on the existence of space-time may be needed to avoid nomic incoherence. And the debate, for instance, between substantivalists and relationalists, even though the exact ramifications here will depend on the concept of matter, and I should add the concept of space-time, of course, as well. Thank you very much. Do you need this?
I'll use it, I think. Okay, let's see if this can work. Sorry. No. Okay, well, thanks Chris and Baptiste for this cool paper. I kind of am completely on board with the basic outlook that space-time, if emergent in this sort of way, is going to be contingent in this physical sort of way. So I'm not going to kind of question the overall claim about physical contingency. I'm going to talk about four different aspects of the upshots that might have. And this was a kind of a long and rich paper. It was 10,000 words, and they couldn't go over all of these details. And so some of these things didn't really come up in the presentation, but I'll go through them anyway because I think they might be interesting for discussion. So first point is about emergent theories which might not be spatiotemporal. So this is kind of to do with the prospect of kind of theories that are about matter and theories that are about space-time coming apart. But one way in which those could come apart would be if space-time drops out of the theories anyway. And this is the most speculative, perhaps, of my comments, but it's, I think, at least possible to think of some of our theories at kind of a high representational level as being not spatiotemporal at all anyway. So this might be kind of theories of macroscopic phenomena, but in which space-time has dropped out of the picture. And here the idea would be where we have quantities like kind of information or other similarly abstract logical or mathematical concepts kind of doing physical work. And my example is in the theory of computation, computable functions, and what sort of constraints those might put on physical processes like the ones that are playing out around us that might not actually be spatiotemporal in character at all. And yeah, so this was a section of the paper they didn't talk about today, so I'll just move on to some parts that they did. But perhaps we can talk about this. So here the point relates to the relation between a high-level description, between a lower-level description at the quantum gravity level being material versus it being spatiotemporal. Wüthrich Baptiste suggests in the paper that we might have an understanding of quantum gravity where at the fundamental level there isn't any space-time, but there still is matter. The behavior of the strings, for example. And my kind of question here is kind of what it takes for there to be matter at those fundamental level, at the fundamental level. If it's the case that we don't have space-time there because what's going on is kind of too different from the space-time that we're used to, the question arises: is there even matter there? Is what's going on there too different from the kind of matter that we're used to? So the kind of question is, what does it take for there to be matter in quantum gravity at the fundamental level? One suggestion would be that we have matter just when we have like a mass-energy tensor field in GR, that there's a conceptual connection between matter and that field. But in these non-spatiotemporal regions of quantum gravity, if we don't have an emergent GR description, we don't have an emergent mass-energy tensor description either, in which case it might seem that at the fundamental level of these quantum gravity theories we've lost space-time. Space-time is going to turn out to be contingently emergent, but matter is the same. We might not have any matter at those levels either. So it might still be that kind of matter and space-time come together as a package, but they're kind of both contingently emergent rather than just one of them being contingently emergent. And in that case we might kind of think that the kind of matter and space-time are both jointly emergent from something else. What might that be? Maybe it's hard to get our head around what it might be, but idealists might say, it's mental stuff at the bottom level. Pythagoreans might say it's mathematical stuff at the bottom level, and that whatever that stuff is, it's not material, nor is it spatiotemporal, but it's still real. So then they both emerge together from whatever that base is like. With the question about relationism, and this they didn't go into details in this in the talk, but my suggestion is that relationism can still make sense in an emergent space-time picture, because we might think of relationism not as something that says kind of matter is fundamental and space-time isn't, but just as the relative claim that matter is more fundamental than space-time. And even if both are emergent, one could be more emergent than the other. So we might think that we've got the fundamental description, and then matter emerges from it, and then we understand space-time as the relations amongst that matter. So we still have relationism. Both the matter and space-time are at the level of GR, which is itself an emergent level, but there could be like further emergence going on within the GR level, as well as the emergence of the GR level from the sub-GR level. And finally, there was this kind of worry about the epistemological status of laws if we were gnomic pluralists. And here I wasn't really getting the nature of the epistemological trouble, so I'm kind of inviting kind of further feedback. But it seems that, depending on the kind of emergence, as long as we don't have strong emergence in mind, if we just have a sort of weak emergence, where there's still a kind of modal determination of the emergent from the non-emergent, then we can use the kind of ordinary kind of epistemology of associated with weak emergence to kind of use our knowledge of the higher level laws to infer to the lower level laws, in terms of lower level laws being such as to be the kind of laws from which our higher level laws could emerge. And I think there's kind of precedent for thinking of higher level emergent laws as being contingent anyway. I mean, when we teach like in schools like one of the first things you might encounter in like primary school physics is the law of gravity, and it's that like everything accelerates down towards the Earth at 9.8 meters per second per second. That's obviously, if it's a law at all, it only is like a law of like a very constrained spatial region, like the surface of the Earth and things in that region. But you know, it's relative to that region. It seems like it's a law. The Earth could have been a bit bigger, in which case this acceleration might have been larger. So it's a contingent local law, but it's kind of law-like in its counterfactual supporting nature and so on. So I think there might be kind of precedent for these sorts of contingent local laws. And all in all, I don't think this gnomic pluralism is as conceptually or as epistemologically challenging as was hinted at. Okay, that was it.
Okay, thank you very much.
Do you want your slides back?
No, I don't.
Okay, well, I'll just leave these.
Yeah, sure. If it's okay, I take a stab at answering them. So, for the most part, I cannot speak for both of us, so maybe there's some disagreement, but as far as I see it, I largely agree with your comments. But let me say a few things in response anyway. So, the first point was about, sort of say, an information theoretic or information-based sort of physics, which may not be spatial temporal at all, and there may be other forms of physics, dealing with abstract or non-spatial temporal sorts of entities, whatever that might be. And I certainly grant that this is a possibility. It's not a possibility I'm very sympathetic to, but it is a possibility, somewhat speculative, that much more physics might turn out to have that non-spatial temporal character, in which case space-time and space-time physics would be emergent anyway from something very different, fundamentally speaking. My take on this is more like, even if you're a die-hard realist about, sort of physicality, materiality, and space-time the old way, quantum gravity may force you into that sort of position, whereas these others might be resisted on more philosophical grounds, perhaps. Okay, the second point, yes, we haven't really discussed it in the presentation today, but it's of course a big question that we need to address. What is it to be material? If we cannot just sort of presuppose it's spatial temporal. Obviously, in most of physics, in GR and elsewhere, it's presupposed that material things are spatial temporal. There may be bodies in space and time. There may be fields in space and time. There's the materiality might be captured by a sort of mass energies tensor, what have you, something like that. All of this is spatial temporal, and it's clear that if we go to the more fundamental, more gravitational situation, we will have to reconsider what the concept of what it means to be material, and there's going to be different options. We don't endorse any particular option, but we highlight the fact this will be a question that needs to be addressed. And maybe the answer will be that material entities emerge just as space-time does, and something that's neither spatial temporal nor material. That is certainly possible. The relationalism and the horizontal versus vertical sort of relationships, I generally agree that a building relation may be vertical, a vertical building relation, of course, that doesn't necessarily have to straddle the sort of the non-spatial temporal realm of fundamental physics and the spatial temporal ones. There could be within the spatial temporal one, there could be some sort of hierarchical organization. Yes, so I don't deny that. We've tried, maybe somewhat too simplistically, to just make a distinction between a relation that does straddle the non-spatial temporal and the spatial temporal, and one that doesn't necessarily, by using the idea of a horizontal relationship, which may not be strictly horizontal, but at least not straddling the two different realms. And finally, about gnomic pluralism, yes, these are good points. Of course, there are local emergent, physically contingent laws. That's in itself is not a new idea, just as the law of free falls surely is a local contingent law. But I take our point to be more radical than that, because arguably, if you're a Humean or a primitivist or a dispositionalist or whatever your favorite analysis of laws of nature is, you can still say, yeah, of course, but whatever is a law of nature is going to be identified at all these levels in the same way, and that there are some laws for which maybe some less fundamental laws and contingent laws arise. That's just the problem of the special sciences in a way. Biology could have turned out to be completely differently. It turns out to be that way because of the particular way the fundamental laws operate and maybe the initial state of the world. And we are considering a situation in which the analyses are going to be completely different at the different levels. It's not just, Okay. I'll stop there.
Thanks so much. We have 15 minutes to remaining. Yes.
Yeah, thank you. That was super interesting. There was one step in the argument for the contingency of space-time that went by me a little quickly, so I wanted to ask you to say more. And that is, the step was, you said, only if you compactify string theory in the right way, you get a general relativistic space-time. Okay, so string theory is at bottom a mathematical structure. And it's quite common in physics to, you've got a big mathematical structure and you say, well, yeah, but these bits of the structure we rule out as unphysical, right? And in less exotic applications, you know what you're doing there, and I don't really have a sense of whether and when you can rule out certain kinds of compactifications as unphysical. Obviously, you couldn't do it, say, all the ones that don't generate space-time are unphysical. That would just beg the question. But could there be other constraints on the compactifications that render them unphysical? This could not be a way that a universe could be that is still string theoretic.
Okay, so there's, as I see it, there's two questions. One I'm happy to address, and maybe one more for Baptiste. So there's the general question of whether we could impose some additional constraints on what counts fundamentally as a truly physical possibility, as opposed to some sort of strange artifact of the mathematics, perhaps, of the theory. And at the level of GR, you can debate, of course, what counts as physically reasonable space-times and what should be eliminated as such. So this discussion could be had and maybe should be had for any theory. I'm of a cautious person in many ways. One of the ways in which I'm a cautious person is by taking seriously prima facie what the mathematics tells us, even if to me it sounds counterintuitive and strange, and would not want to sort of too strong-handedly rule out something just because it goes against my intuitions. Certainly something we wouldn't want to do is sort of just say whatever does not give rise to relativistic spacetimes is to be deemed unphysical, because that would truly beg the question against our point. And if you accept that, you should accept at least the possibility that there are some models which do not give rise to relativistic spacetimes. And now there are some very technical reasons in string theory why some of these models do not give rise to spacetimes. The same happens in loop quantum gravity and in causal set theory, but they are somewhat technical. We try to be a bit more precise and substantive in the paper. I don't know whether that's good enough an answer. Okay.
Yeah, thanks, Chris. Actually, my question is very similar to Peter's. Frame it a little bit. You have this picture of this slide with green and blue, right? Or I don't remember the order. And you said that the things outside the shaded region in the bottom level that do not map into like models at the top level. Those, the fact that those exist, is kind of enough, or more or less enough to have contingent space-times, right? Because is that fair, or I misunderstood that?
It's slightly more complicated because there could be the possibility that these things do not correspond to a general relativistic model, even though they're still spatial temporal in some sense. In some sense that violates GR.
They're still spatial temporal.
There might be. I mean, this.
Okay.
So if it's outside the shade region, it could be spatial temporal or not, even though it's clear that it's not going to have a space-time, emerging relativistic space-time model as a counterpart. So in that case, we have to argue a little bit more carefully and to show that there exists at least some models among those which are not spatial temporal, of which we should not think of as really relevantly spatial temporal. Then we have established what we want.
And then, do physicists, are they happy with those? Like, because I was imagining what kind of experiments or things, like, because those are more spatial temporal, then it's very hard to see what kind of evidence you could get for.
You mean empirical evidence?
I guess, yeah, because theoretical maybe, but.
So empirical evidence would be awesome if we could get that, but
Yeah.
that's pretty much out of the picture for now.
Yeah.
And that is a big problem, and everybody accepts that this is a big problem. So of course we would like to have that. So there's theoretical evidence, there are arguments, there's reasons to think that such models exist as we showed in our paper, in two approaches to quantum gravity. And I'm confident that we could do the same argument, the same analysis, the same outcome for other approaches to quantum gravity. These are theoretical arguments. Now, empirical arguments are going to determine which of these approaches, if any, is sort of getting things right, or maybe almost right. And then we would know which way to go. And it's certainly a possibility that we will end up with a theory that does not have this conclusion. That is a possibility. I think it doesn't look like it right now, but it's a possibility, it remains a possibility. Once we have empirical evidence to help us with theory choice in quantum gravity, we can more determinedly look at that particular approach, and I will bet that it will have the result that space-time is physically contingent. But it's a bet.
Hi, thanks. My question is, I take it, let me know if I'm off base there, that neither our quantum field theories nor our string theories are completed physical theories, in the sense that they don't maybe deliberately take a stance on the measurement problem. Could it be that if you want to take a stance on the measurement problem, you might find that you want to appeal to spatial temporal resources there to do that? For example, non-relativistic quantum mechanics, if you want to formulate the Flash ontology for a GRW, you find that you appeal to space-time as the location where your flashes are located. Could something similar happen for string theory?
This is an extremely hard question. You're certainly right that none of these they're research programs. We should think of string theory, causal set theory, Lugano gravity, all these different things as research programs. They're not really completely worked out theories where all of their implications and so forth are understood, let alone how to solve the measurement problem in the context of any of them. There are some suggestions, some people who have published papers where they propose how you could, for instance, articulate the Bohmian version of loop quantum gravity, and because it's Bohmian, and Bohmians claim to solve the measurement problem at the non-relativistic quantum mechanical level, then presumably, by analogy, the Bohmian loop quantum gravity will solve the measurement problem in quantum gravity. these are more suggestions and hopes than really fully worked out arguments. And it's so difficult to really get a firm grasp on these questions. But yes, they loom in the background, no matter about that.
Okay, thanks for the presentation. In the first part, you talk about the possible worlds, and in this world you don't have spacetime relations. So I was wondering which is the world-making relation for those worlds, and how you build the worlds in your account.
Which relation? Sorry.
Which is the world-making relation for how the world in this case? Because usually you can build worlds from, okay, if they are spacetime related or somehow. But in this case, it's not clear.
Okay. Yeah. No, of course. I've written a paper that, by looking at studying causal set theory, you have a problem if you're Lewisian and you want to sort of use your spatial-temporal relaxly, spatial-temporal relations, the world-making relations, and so on and so forth. So that is a valid question. Here we somewhat side past that question by just saying, like, look, a world is just a pair of models, a fundamental and an emergent model, even though the emergent model might actually be absent. And what these models are is given to us by the physics. So if you want, the model-making relation is given by string theory. Whatever string theory tells us is fundamentally there, physically speaking. That's the world-making relation, if you want. If we look at causal set theory, it's the causal set theory fundamental physical relation that is the world-making or model-making relation, and so on and so forth. So the answer is going to depend on the research program.
Question? Yes.
Thank you very much for the presentation and also for comments. Sorry, my voice. Okay. My question is related to your beginning of presentation when you say that with new physics can emerge from nice existing physical theories of physics like GR and so on. And of course, these existing physical theories are fundamentally based on ontological status of same ontological status of matter, energy, fields, and so on, which ontology represents fundamentally. My question is, can you admit as a metaphysician that new theories or new physics can emerge also from, let's say, if information will come on the stage, ontologists, with the same ontological status, if it is possible? It is your opinion. Thank you.
So, in principle, yes, sure. I don't see why not. Of course, that's a possibility in some sense. For different reasons, I'm not very sympathetic to approaches of sort of understand everything in physics information theoretically. However, it depends what you mean by information. If you mean by information something that's perfectly sort of implemented or instantiated in the physical world, then I don't have a problem with that. There might be a useful way of actually talking about the physics. If you think of information as something abstract, then I think you're just confusing mathematics and physics. That's, if you're doing physics, it must be in some way physical and concrete, not abstract. Otherwise, we're just doing mathematics or something similar to it. But maybe I was just sort of too narrow-minded about it.
Okay, thank you. Okay, let's start for one more question. No, so in that case, let's close the discussion. Thank you very much once again.